Well, good morning, my chemistry kids. It is Monday morning. It's about 10:30, and I've already recorded the lab when I went up to the school. Shh, don't tell anybody. Shh, okay? And the lab that you're going to do the analysis on is one of my better titles, if I may brag, the exceptional analysis that is oh so fine of the reaction rate of iodine. And if that doesn't make you smile, then I don't know what does. I really don't. I mean, that's just a cool title. I'm sorry. Okay, so here's what we're going to do. And this is all just kind of background information. And this is stuff that you already know. But what we're ultimately going to try and find is a couple of things. Is that the first thing we're going to try and figure out is that what is the order of the reaction. Now, we're actually going to look at three different concentrations that we're going to manipulate. Concentration of the acetone, the concentration of the iodine, and the concentration of the hydronium ions, okay? Otherwise known as the acid, which in this case is going to be hydrochloric acid. 1 molar to be exact, if you really want to know. So the first thing is I want to try and figure out is that what is the order with respect to each one? Is it zero order? Is it first order? Is it second order? Whatever that is. So that's the first part of the lab, is to try and figure out what these variables are. Then once we get those orders, then we're going to try and figure out the activation energy. Okay, so that's going to be the second part of the lab. So what this gives you is this little bit right here is going to be key. So to try and find that activation energy, your value of R has to be the ideal gas law constant that's in joules per mole Kelvin, okay? Because you can't use the one that's in liter atmospheres because oddly enough, the units don't work out. So we'll get to this later, but make sure that when you do this calculation that you're using this value for your R, okay? And technically it's 8.314. You can use 8.31, whatever works for you. Okay. So here's going to be the basic reaction that's going to take place. And this is a situation where there's also some, like we talked about on Friday, there's some secondary reactions that are taking place. But this is the overall reaction. So basically what's going to happen is that your iodine is going to react with the acetone. And basically what's going to happen is this. At the end of this CH3, okay, what's going to happen is that you're going to basically kick out a hydrogen, and one of the iodines is going to take its place, okay, which is why, hold on, I kind of need to see this. So what's going to happen is that right here on the end of this carbon structure at the end, you're going to kick out a hydrogen, and iodine is going to take its place. So that leaves I1 minus. So what we're going to do is we're going to take advantage of the fact that this iodine has a dark brown color to it. But everything over here is going to be clear. So as the iodine is getting used up in the reaction, what you're going to see is that it's going to fade. And so we're going to stop the reaction in terms of time when the solution goes clear. That means that we don't have any iodine that's left over. So we can't physically measure the concentration of the acetone because it's a clear solution. So what we're going to do is we're going to take advantage of the fact that the iodine is being consumed. That's going to go and form this molecular structure over here. Now, here's what's going to be important. You're going to be kicking out hydronium ions. Now, at this point, you're going, wow, okay, so the hydronium ions are a product. And if that's the case, then, Mr. Burkamp, why are we manipulating the concentration of the hydronium ions? Why isn't the concentration just based upon the concentration of the acetone and the concentration of the iodine? That would seem reasonable. Why do we worry about the hydronium ions? Because this is a classic situation where this right here represents the overall reaction that's going to take place. There's a secondary subreaction where you reach an equilibrium, and the hydronium ions are actually a part of that secondary reaction that could potentially affect the rate. Okay, so that's why even though the hydronium ions aren't listed in the overall reaction, we're still going to worry about them because of the fact that it's going to play a role in a secondary reaction, well, like we talked about on Friday. Okay, so here's going to be the big thing. What you're going to try and do, and this is going to be in right up on the lab, you're going to try and figure out what these values are, what the concentration of the X, Y, and Z. So I'm going to scroll down, and what you're going to see is that on all four, we're going to run 4 different reactions, and we're going to vary the concentration of the acetone, the iodine, the hydrochloric acid, and the water. And this is what I've showed you in the video. And then what I did is I went through and I ran this reaction, and then I recorded the times for these trials to run. And you run 2 trials at the same time, and this is the data that I got when I ran these 2 reactions. So what you'll notice here is that when you add these together, 10, 10, 10, and 20, 10, 10, 20, 10, 10, 5, whatever, what's happening here is that you are keeping the total volume as 50. That was horrible. You guys can't read that. We are keeping the total volume as 50 milliliters. So that's going to be a key part of this. So by changing these values, we're going to change the concentrations of what's going to happen down here. Now, I want to make sure everybody knows what's going on here. So what we want to do is we're going to calculate the concentration of the acetone just after everything has been mixed together. So to do that, we're going to use the idea that M1 V1 equals M2 V2, and the total number of moles is going to stay the same. So I'm going to do this first one with you to make sure that you can get this number. So we started off with 10 milliliters of a 4 molar solution. So we're going to take that 4 molar solution times 10, and then that's going to equal that molarity after it's mixed, which I don't know, but then I know the total volume is 50 milliliters. So if I take 4 times 10 and get 40, and then divide that by 50, that's how I get that 0.8. So what you're going to do here is that to get this concentration of the iodine, you're going to do the same thing. And what you're going to see is that once you get those, and you're going to do this for all of these, then what you're going to do is you're going to have all of this filled out. And then you're going to have these concentrations. So what that's going to allow us to do is that when we compare these mixtures, we'll be able to isolate 2 columns that stay the same, and then we're going to change one of them like we did on that very first rate law assignment when you're trying to figure out the rate law. Now, to get this rate, we're going to base this off the concentration of the iodine, because conveniently everything here is in a 1-to-1 ratio. So this is what we're going to observe. So this concentration of iodine is going to be, you're going to know what this concentration is going to be when you start out. You're going to know how much time it's going to take. So this is going to allow you to get that as molarity per second. So what you should see on all of these values here, these should be something around 10 to the negative 6, 10 to the negative 5th, something like that. Okay? So if you do this right, that's what these rate values are going to be, 10 to the negative 6th or 10 to the negative 5th. So once you get those variables set up, okay, and once you get those molarities, then what you're going to do is you're going to isolate these just like we did. So this is just this big drawn out procedure. Now, you might have to get a little bit creative with rounding, because in all the data that we've kind of looked at so far, it's been exactly like 2 or 4 or something like that. This one, because we're working off real data, this might not work out to be exactly like 4. It's going to be pretty close, okay? It's going to be to the point where it's going to be close enough where you can certainly round it to a whole number. So it might be like 2.1. and you could round that down to 2, or it might be 1.8, and you could round that up to 2. Okay, so don't flip out on that if things don't work out exactly, but they're going to be pretty close. Okay, this is kind of a home run lab, and I really wish you all could do this lab instead of me just having to film it. So here's what you're going to need to do. You're going to take the average time of these. Okay, put that here. The temperature stayed the same, which was 20 degrees Celsius. We're going to need that later on. And here's what you're going to do. So like on this one, substitute the initial concentration. So this is going to be like K times, and the whole key to this is that you're going to go up to equation 3. Okay, so if you scroll back up and you find equation 3, that's this one. So you're going to write this in terms of, oh, here's the concentration of my K, concentration of my acetone, which you're going to know, the concentration of my iodine, and the concentration of your hydronium ion. So you will be able to actually substitute in those values. So here's what you do. And on the first one, I take you through this. I'm going to tell you, you're going to take rate 2, and you're going to divide that by rate 1. So you can have K, K, concentration, 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 X, X, Y, Z, X, Y, Z. And what you're going to do is you're going to make two of these concentrations cancel out, and then you're going to K's are going to cancel out, and then you're going to be able to figure out what the value is for X. Okay? So then you're going to do that with Y, which is going to get you you're going to solve for the concentration of the iodine, and then you're going to solve for the concentration of your hydronium ions. Okay? So let me give you a hint. One of these orders of magnitude should be 0. Okay? So if all goes well, I'm not going to tell you which one. You'll have to figure that out on your own. But one of these should be a 0 order. Okay? If you don't get a 0 order, something has gone wrong. Then, once you know the value of the rate, okay, then you're going to go through in each one of these and you're going to solve for the value of K. So this is going to be the rate of 1 divided by the 2 that are not 0 concentrations. And then you're going to do the same thing here, same thing here. So this is going to get you 4 different values of K, and then you can take the average of those. That's what you're going to use down here. So then here's going to be the cool part of this. Is that, again, if you were actually doing this lab, I'd let you guys pick these volumes. But I went through and I picked the volumes for you, and I ran this reaction. So I said, okay, I'm going to start with 20 milliliters of acetone, 20 milliliters of hydrochloric acid, 5 milliliters of I2, 5 milliliters of water. So what you need to do is you need to go through and you need to calculate these concentrations after they're mixed. Remember, the total volume is still 50. Then, knowing those values, then you're going to go, oh, R equals K times the concentration times the concentration. So you're going to know the numbers that you can put in here. Then, once you get this, then you're going to go to equation 5, okay? And equation 5 is up here. So at this point, you're going to know the rate, you're going to know the concentration of the iodine, and then you're going to solve for time. Okay? So that what you're going to do is say, okay, based upon that rate and based upon this initial concentration of the iodine, this is how long it should take. So when I actually ran the lab, I observed it to take 26.3 seconds. So if your predicted time here is vastly different from 26.3 seconds, you've done something horribly wrong. Okay, now here's the third part. So on the third part, I chose reaction number 2 as the one that we're going to use. We could have chosen any of them. I just went with reaction 2 because that took the shortest amount of time to run. So what I did is that I ran this reaction at 3 different temperatures. I put it in an ice bath, and it took 210 seconds, which took a long time because everything was so slow. The molecules just weren't colliding very quickly. I already had the room temperature data, so there was no need to do that. And then I warmed the solution up to 35 degrees Celsius, and that went really, really quick. That only took 18 seconds. I didn't even have time to like pour it into different test tubes. So what you need to do is you need to change this temperature into Kelvin. Okay, remember I gave you this handy dandy little hint up here. Take this temperature, add 273 to it. That's going to get you this number. So what you're going to do is you're going to calculate the rate at the 11 degrees, the room temperature one, and then the 40 degree ones. So again, you're going to know the concentrations of your iodines, and you're going to know your time. So that's what's going to allow you to get that rate. Then you're going to solve for K. So K is going to be changing here. So if you look at this in terms of R equals K times the concentration times the concentration. The concentrations on both of these, on all three of these temperatures were the same. So the only way that you can have a faster rate is if you have a bigger value for K. If you have a smaller rate, you have a smaller value of K. So you're going to go through and you're going to calculate these values of K, then you're going to take the natural log of K, and then you're going to take the 1 over the temperature in Kelvin. So then, on another sheet of paper, graph it, whatever. Now, on your graphs, some of you are using like Excel or whatever. Here's the problem for me. If you do that, then it's tough for me to grade it, because then I have to look at open that up in another program. If you want to do that, that's fine, but just make sure that you send that as a separate document, just because of the fact that, you know, I've got to I can only grade stuff that's in like as a PDF file in using this program here where I can write on the screen, because this is what I use to grade it. So just, I don't know, just figure out how to draw that line. But here's the whole point, is that you're going to draw this line of best fit. So if you're actually going to draw this line out, listen to me, Vin and Chris. You have to draw this out, and you have to use a ruler. So, because that's how you're going to find that line of best fit. And I want to see how you find that slope. I don't care what you do. Here, show me how you're going to get that slope. So then, once you get that, then you can find that activation energy. And again, I tell you up here to use equation number 2. So you're going to go up towards the front of that lab, solve for the activation energy, pay attention to the signs of the slope. So then, once you get this, and you might have to do a little bit of reading, so don't flip out and go, oh my God, what are the 4 factors that determine the rate of a chemical reaction? I'm just telling you, I'm just going to give you a hint. You might go out and do a little bit of reading on the lab. I'm just telling you, you got time. So anyway, and then you've got a bunch of questions to answer on all of that. So here's the only thing that I want scanned and sent back to me. I don't need the first 3 pages sent back to me, because those are just instructions. I don't want to see them. I wrote the lab. I know what they are. So what I want to see is page 4, page 5, page 6, page 7, and the graph. Okay, that's what I need back to me. Anyway, so there's all of that. This lab is going to be due on Wednesday. This is kind of the big culminating thing. And then I will send out the review. The test is going to be sent out on Friday. So there's that. All right, kids. I will see you in the Google Meet chat.